Oops, no. I don't know why it does that to me. For some reason, Barrow's TV comes up as my first. There we go. Okay. I'll let you all decide. Do we want to start with our LLRBs, or do we want to look at the Batman thing? Batman. All right. How'd we do with it? I have no idea. I haven't seen them.
Oh,
So
I guess I'll stay here then.
what's that?
I was trying to do like test correction, but I don't see him in his classroom. So
It might be up in like his office upstairs. Run up there and check. Sure. That's what I would do if I were you. But yeah, I'd go up there and check and see if he's up there.
thank you.
Yep. Who got it? Okay. What do we want to do? Daniel?
So I like before like you reassigned it to us,
Yep.
I was doing it, like I was updating like the position.
Mhm.
And then I realized that it wasn't working because it was like the binary search of the two corners, I had to update like the ends. Like it's like so the ends on top and bottom.
Yep.
So I started updating what I called it left, right, floor and ceiling.
Mhm.
But I tried that, but I kept getting it wrong, and I'm not too sure why.
Okay.
I tried to debug it and stuff, I'm not sure. Can I share my screen?
Sure. So we'll collectively debug. This won't really work for people online, but that's okay. No such luck.
So like I made left 0 like on the left side, right is like the width -1. Then the floor is like the bottom, ceiling is like the height -1. And then if the direction is up, I thought that like the floor, since it's up, would go up by 1 because I'm changing like y is 4 like top plus bottom over 2, like the binary search thing, but I kept getting it wrong. Couldn't figure out why.
Okay. Anyone see any issues? Scroll up a little bit. Let's just see what else you have. Oh, it's just okay.
Oh, it's because when you're going, yeah, when you're going up, floor needs to be Y0 -1, not +1. And
Wait, what?
because when you're going up, oh no, it's not floor, it's actually wait, it's oh, ceiling +1, because if you go up, your ceiling goes up, right? Because the ceiling is like
But what if the ceiling is at the top? That
Did you take the min amplitude?
Say again, Jackie.
You take like the minimum of like the Y0 at ceiling.
How did other people get it to work?
no, it should be ceiling equals Y0 -1, because ceiling is like
-1.
yeah, because ceiling is like the bottom of your grid. So if you want to go up, you have to -1, because
It is?
the index is like
He's putting floor as the bottom. Yeah,
Oh, wait, top left is 0, 0.
yeah.
Oh, okay, never mind.
You flipped your coordinate grid.
Yeah.
So it's like it's the grid is like processing.
I did it the other way around.
Yeah.
I didn't even realize that.
it has to flip.
You just flip the yeah.
Oh. And it's up, ceiling. -1, it's down for like bottom +1. I'm going right.
Yeah.
Oh.
So you just got to flip your math in terms of thinking about which direction you're headed with your y coordinates. Why don't we do this? Who's got a solution they want to share that works? Gordon, go ahead and pull it up.
Oh, mine is
Basically the same.
Okay. So Daniel, let's see if this can help.
Well, actually, I saw Daniel use contains, that's actually smarter than me using equals for every single one.
Bless you.
Yeah, so basically, I set min width as 0 and height as 0, max width as 30 minus 1, and max height as h minus 1. Because it's a 10 by 10 grid, but the max height is 9, and the max width is 9, it's not 10. So it's gonna be minus 1. And then if it's up, then you have, then max height has to be, you subtract it by 1 to go up. Yeah, because you're going, yeah, because you're going up. Same with right. Min width, it just goes 1 to the right. Same with the other ones, down, left. When you have two directions, just use both movements in the same thing.
If you did normal if statements, wouldn't it do that?
Yeah, if you use if and then use it contains, then that's actually more efficient.
Yeah, I was gonna say you'd have to use, we have to be careful with contains because you'll get these two, right? If we use contains D and DR, then we run into trouble.
No, but if you do two long dir dot contain theme, it will run this one. And then you can also have another if statement, like if it contains R, it'll also run this one. So if you have.
Oh, you're right,
DR,
you're breaking them into two pieces,
Yeah, it'll still work.
yeah, you're right, sorry. Because you're doing them both separately, yeah.
And then here's like the binary search part. So. Yeah, so each time the boundary becomes smaller, you gotta know. To find like the most efficient solution, you have to go to the middle of like the boundary, the new boundary. And you have to like go inside the boundary also. So yeah, you go inside like the middle of the boundary, but you don't know where in the boundary the bottom is, but you know it's somewhere in the boundary. So you go to the middle of it to find like the most efficient solution.
Nice, did I give you guys a place to drop the code for this? I didn't, did I?
In a text box.
I did, yeah, okay, good. Okay, did anyone do anything radically different? Donald, Ethan? Tony? Same, okay. Okay, so hopefully for those of you that didn't get it, hopefully it gives you at least a sense of sort of where to go with it. Okay, back to our LLRBs. So let's sort of revisit this. I realized I didn't actually record this last time, so we'll come back and record it. So essentially, again, we're going to take our what would be our 2-3 tree, right? And we do what with our well, again, what is this? What is this one? What do we call this? See, that's
3 nodes.
it's a 3 node, right? Again, confusing. This is the 3 node. Why is it a 3 node? 3 children, right? 2 things in it, but it's a 3 node because it's got 2 things. What do we do with our 3 node?
We make like the smaller one, the child of like we make B the left child of it.
Yeah, Mary, what were we gonna say? Yeah, we red link, we drop the left or the smaller, as Daniel was saying, to down to the left. It carries with it the 2 children that are on that side. So this is hopefully fairly straightforward, and we just sort of consider these as red links. So whoops, wrong direction. We go here. So we have the 2-3 tree on the left, and we get the corresponding BST, red black BST on the right. And again, what do we know about each leaf node in this thing? Say again, Tony. Yeah, the black distance to every leaf node is the same. So if I go to A, obviously A is further distance in total, but I have 1, 2 black nodes or black connections height to M, as does every other leaf node. Okay, so 2 black connections, and the reds just do that. Okay. So some properties of LLRBs. So first of all, do we want, we're gonna do this slightly differently. We're gonna do, should we do that, Tony, Ethan? We're gonna reload that one more time. Everyone jump up. Make sure you have a marker that works. That marker. Daniel, Tony, Jackie, you'll join them. Ethan, Alex, Logan. All right, Gordon, Donald. Those three groups. Grab some board space. So you're drawing the LLRB that corresponds to this tree. Markers, you guys have markers?
Oh.
Are there markers back there or no? You got a marker.
But then, yes.
Oh, Donald, totally figured her out.
You're right. Right. And you would have a couple. Okay, and then. 8 split. Yeah, so. One. Which one that was?
Yeah, so for, that's good call. So for your red link, just do two arrows, 2 lines.
Oh, yeah. Oh, that's just. Yeah, sorry. So. I use 2 lines. We matter. We. No, it's like this. Yeah, you pull. I did it wrong. I think S is not smaller than.
Use a double line to connect your, there we go, US.
You are at each Oh, shit. Someone who can't remember the alphabet. What does it matter?
There's always the song, Tony. There's always the song to get you through. When in doubt, sing it out.
Double connection. Because it's left. It's left. So you want to do.
So what's our trick to make sure that we've done it right?
This black.
Check your black nodes to your leaves.
This is a good window, right? Yeah. There we go. Sorry, like here, maybe like. It goes there, it goes here. Right, this big, yeah. And then X and Y.
Cover the marker. Cap your markers. Hate to be stingy with markers, but you know.
But Y is greater than. Yeah, so like the that. Oh, so really, that's like that. Yeah. X, Y. And that X is.
Okay, look around. Make sure we all have the same picture. All got the same picture? Excellent. You guys can stay standing. So it should look like that. I'm slightly colorblind, so this is harder for me to see. That's a red link. That's a red link. That's a red link. Yes? Okay, cool. Yep.
You like switch X with Y?
Nope.
No.
Nope.
Well, you can put Y on the right. Oh. It's left leaning. Oh, right.
Left leaning. So again, does it have to be left leaning?
No.
What could it be? Right leaning, but you got to pick one or the other, right? Or else we sort of lose the whole point of it, right? So we just arbitrarily pick left leaning. Therefore, everything has to be for red link. Where does our red link go? Left. Okay, we just decided that arbitrarily. And it's going to pop up a couple times today. Join a call. Wait, what? Huh, okay. All right. So your next job is to we'll call these A, B, C, and D. Write down which of these, decide which of these are valid left-leaning LLRBs with a 1-to-1 correspondence to a valid 2-3 tree. A, B, C, or D. You can just write down which ones. How about it? A little bigger? Oh, that's so much better.
It's definitely
It's not a two.
the connection to
Yeah,
G.
so.
And then
it's
the
all
beat now, it's like,
If B, I just wanna go one, B. A and B.
Probably.
Yeah. It's not one black.
Or yellow.
No, it's not these two, see, it's black, those are all things. Yeah. Yeah. So just. Yeah, I see.
Well, I'm kind of thinking. No, actually, it's not. Why doesn't
You would have
to. You can't connect their A and
And it's not a two, it's a two.
No,
Yeah.
because how do you find A, right? Just like.
So what, how are people making their decisions? What do you mean? Two? Well, B, C, and D are all the same. Aren't they? In terms of distance to the root?
Or yeah, but like the block.
Black distance to the root. Okay, so our leaf nodes, black distance to the root. Well, what about the first one then? It's got the same black distance. Say again. Why not? So A, B, and C are all in the same node, right?
Yeah.
Okay, there you go. So 3 nodes in here. We got a 4 node in here. This thing would look like this. What's the 2 problems with this? It's not a 2-3 tree. They're not the same distance away. And what should this have? By definition, it should have 3 children, right? It can't have 1 child, given the structure. This one is it a valid binary tree? Can't really see what's going on underneath there. It is a it's a binary search tree, right? But it's invalid because it's not balanced. And we know it's not balanced because we have different lengths to our different depths. Yep. Okay. So D is the only one there. Okay. How about this one? Everyone write down. How tall is the corresponding LLRB for the 2-3 tree? You don't need to worry about the 3 nodes you pick. You can see that they're 3 nodes, right? The ones that are there. But he did color code them.
So. 1, 2, 3.
So like.
On the right. And that comes a lot, how would you?
The 2 or 3.
You pose.
Yeah.
1, 2, 3, 4, 5, 6.
You don't have to draw the whole thing out.
6. It has to be the same.
Oh, how tall?
Does not, because those are that.
Yeah.
Like the right side.
What do you mean how tall is it? Are we including like are we talking like black node distance or like? red?
No, so this one is the red, like black and red, right? Because we know theoretically how many black nodes will there be to every leaf? To every, there'll be 3 black, because there has to be, right? To make it an LLRB, there has to be 3 black. So it's total height with the red.
Long as you go the longest path, it should be
Yeah.
fine.
So
1, 2.
No, it's.
And then as you.
Wait, 1, 2, 3.
So.
Look at this.
4.
1, 2, 3.
That's one more.
So one recommendation is instead of drawing out the entire tree, you just draw the longest path. So draw the longest path out if you want to draw something out.
No, okay, let's draw the longest path, so O. And S, so no, it's left leaning, so that you. Here. Wait, no, what do you do when it's left right? You drop that.
Right above it. These are like like
Oh, there's a second. Oh.
That's why it's all like that's it.
Now.
I don't think it is actually, I was told. Well, ours.
Yeah.
You wanna draw that?
Oh,
1, 2, 3, 4, 5. Only
States and market.
Wait, what about? Wait, why do you two people in that trouble? Wait, so, okay, if it's you on this side, what's on this side? Then we have.
Jackie,
Oh, the cheat, the cheat.
you can go.
Okay,
If you need to do that, do that. We appreciate your company, but yeah,
Okay, I'll go help you, I guess.
Huh?
I'll go. help
yeah,
you.
just go chat with them. You can leave your stuff here if you want to. You can take it, whatever. So what do we have? We have that, we have 5. What do we got for a distance, a height?
4 right now.
Okay.
I think we have.
Again,
Wait, where's Josh?
just draw the longest path. You don't need to draw the rest of the tree. Whatever.
1, 2, 3. But I think it's on there.
You don't count that. Okay, let's just try that.
You don't need to draw the other side. Just draw the longest path, right? Do we know what's gonna happen? Everyone's eyes up here for a second. Do we know what's gonna happen over here? What's gonna happen? D comes down and to the left, takes with it what? B and G. So we just add 1 to the height. So we had 1, 2, 3. Now we have 4 on this side. Ignore this side. We know the longest path is gonna be on the right. Be efficient.
U or S T. W B probably. So wait, I'm missing the T. Where's the T? Q, the Q or S T, and then isn't it like? The T three true. When they like T U. Like
Just draw the longest path. Stop, Tony. Daniel, stop. Do you have the longest path?
that's where we're drawing it.
No, you're not drawing it. Can T or anything off you be longer?
Oh
No.
You should go up left side. The one middle. Q or R and then Q or and then K.
Yeah.
Q would be. Yeah. Just got it. So then we'll have to draw this. Oh, no, yeah, because they're greater.
Just count the number of links. Okay, what do we get? 5. This should be simpler than this, right? Because what happens here? S comes down and to the left. It takes with it what? Do I even need to deal with you anymore? No. Do I need to deal with this? No, I don't, because I know that S drops down and I have another 3 node here, right? S comes down, carries with it these 2, and then what happens? Q drops down. So I get 2 red links in there. Okay, so it should look something like that. Does it matter the length of the link? No, they're visualizations. It doesn't actually matter at all. You could put them on the other side of the room, or you could put them on top of each other ostensibly.
Here they have the same flag.
Sure they do.
Yeah, still do.
I haven't changed any black distances. Right? 1, 2, 3 to Q. It's got to be 3, or else I've broken my own rules, right? LLRB has to be 3 black links to every leaf node, And if I don't have that, I don't have an LLRB. Are we good, Tony?
Yeah.
Okay. Okay. So now we're going to implement these things. Does it make sense to get our bushy, our LLRBs from taking a 2-3 tree and then just converting it? Why? Because what do you think? Yeah, I mean, this is the structure we want, right? And this is sort of easy to visualize. So that's all it is. It's just making sure that we actually get the correct structure in our LLRB. A lot of people won't go through the 2-3 tree to get there, but I think, as does he, that this just helps get us to there. Does that make sense? Okay, so this is a helpful way of being like, oh, this is the 2-3 tree, and this is how I'm going to construct my LLRB from that. Okay, so the way we're going to get there, yep.
I thought you said it's really hard to like 2-3 tree.
It is. We're just going to use it as a mental model.
Oh.
We're not actually going to implement the 2-3 tree. Yes, you're correct. We're going to use it as a mental model to get us to our LLRB. Okay. So there's always a one-to-one mapping between our two trees. Okay. So we're just going to pretend that we're doing a 2-3 tree and do our rotations from there. Okay. So should we use a red or a black link when inserting? Which one? If we add E to S, which way do we want to go? So we want this. What's the corresponding LLRB? Or 2-3 tree, excuse me. What's the corresponding 2-3 tree? They're in the same node. So it should be a red, right? This is why we use this corresponding mapping. Because if I have a 2 node, I should have a red link. Yeah? That make sense?
Oh.
Because I'm always going to think 2-3 tree first. What's the 2-3 tree to look like? Oh, then I drop down into the left, I get a red node. Okay?
From the 2-3 tree, can you visualize an LLRB like just in like a 3 node and you just kind of and it's like red.
That's what we're about to see. From a 3 node? Or
Or where there's 2 in there. You know,
with 2 things in it? Yeah.
Yeah.
So anytime I have this, this is what I am visualizing.
Yeah. Yeah.
Is that what you're?
yeah.
But it's got to be a red link, right?
Yeah, red link.
Yeah. Okay. Okay, so we have leaf E, we insert S. What should this thing look like? What is the problem and what do we do about it with E and S? Because I've inserted S, so in a normal binary search tree, where would S go here? But hang on, where would S go? It would go down over here, right? I connect it down here. Does that give me the appropriate structure? Why not?
Same depth, one now.
Because it's right leaning.
Because it's right leaning, right? This thing's off to the right. So I want to visualize this. So what does this look like?
Is it like
X is on top, E goes to the left.
S is here and E is over here, yes? Do we understand how the 2-3 tree helps us visualize these things, hopefully? Right? So what we really need is that thing over on the right. So we're going to, how do we get there? Rotate left, E. When we rotate left, what happens to E? Down to the left, and S comes up. So now we understand why we talked about the rotations last class, hopefully, right? So we're just going to rotate left. That's all we have to do when we have a right node. Okay, finally, we'll represent a temporary 4 nodes with 2 red links. We've got a temporary, so we'll see what happens in a second. We're going to temporarily violate our left leaning. So we add Z to this structure. Where would Z go when we add Z here? It goes just like this, yes? Is this the appropriate corresponding structure to this?
Yeah. No.
Well, why no?
Because you can't have 2.
You can't have 2, we can't have 2 red links. But again, we're going to temporarily violating that rule. Is this the correct structure?
Yes.
Right? Because down here, what would happen? S goes up and these 2 become children, yes? Okay. So how do we fix this?
Oh, you see like red link, like 1, 2,
Yes, we're actually, what we do is we flip
Can
these.
you rotate it?
Do we want to rotate it? Is this the correct structure?
Yeah.
It is. What's the problem?
It's just like you can have two, I mean.
Two red links. That's the problem. Where do I want the red link?
D to S.
I want this to be a red link, yes? I flip them. You can essentially just wrap your head around the fact that I'm just gonna say, hey, I'm gonna flip these up here. The link, the red link, not the links. We're gonna say these are black and this is red. Yeah, Jackie.
So on the bottom one, if you push S up, right?
Yep.
And then you want to separate E and S, then E goes to the left of S, what's that red? After you push S up to like B.
S doesn't go up to B, S goes into its own node. Just like this.
It's like, but like if you have like a normal 2, 3,
A normal 2-3 tree, yes. So S would go up to B.
and you would have and then if you do that into an L or B,
Yeah.
it would be a red link to S.
Yes. But just hold off on that one. We're not quite there yet, Jackie, but you're right, yes. You're taking one too many steps. Let's just focus on the fact that we've got 2 red links. We can't have 2 red links. We're gonna flip them, okay? We'll see that in a minute, okay? But this does give us the correct structure, right? Okay. So again, we inserted E, okay? So where's E gonna go here? So it's gonna go left over here, like this. Okay, but we just saw this with our LLRBs a minute ago. Is this correct structure?
No.
Now, so we want this, right? So if we think about what we have over here to start, we've got this. Is this correct compared to our 2-3 tree? Whoops. What did I just do? Did I go backwards or forwards?
Like that,
You want that, you want that.
Whoop, there we go. Okay, so is this correct?
yeah.
What should happen to S? It should drop down to the left. So that's correct. E should go here. And this is the appropriate 2-3 tree. So what should this look like?
S goes off. So S goes.
S should be where? Where Z is, and Z should be to the right. How do I get there? From here, how do I get to what the correct structure should be? Rotate right, Z. Z will go where?
Down.
Down to the right, S comes up. And then it'll be S here, Z and E. Does that sound correct? We will have 2 red links below again, and we'll see that in a minute. But we get that. So we're back to rotate right Z, gives us that structure over on the right, which is the correct structure, just the wrong red links. Okay. Last one here. We have a temporary 4 node. What should we do? So have at it. Go ahead and draw this one out. What would 2-3 do? Oh, sorry. What would 2-3 tree do?
So we start with the one with the top left.
We're trying to fix, we're trying to split the.
Well, B goes up to G. This is sort of where Jackie was talking about. What happens once we get to
But it's left. leaning.
over to the right?
Wait, this is left leaning, so
Just see your place.
G can't go down.
No. Wouldn't that
Oh,
be
would it
like
just
a
be-
red link?
Yeah, like-
Draw it out.
Here.
Oh, I think we have. Yeah, that's right.
Like this, right? And then everything else is fine. For HC and.
Wait, some kind of reason that ego is up with him, just like.
I think this is the right one. I'm pretty sure this way.
I mean, like, why would it go up and go down?
Yeah.
It's like left and right.
So it's right one. So
When you have,
one.
when you have PG and D's don't matter, like. I mean, like,
But this works for me. They're all the same.
Right?
Yeah. There's nothing happening.
no, we have, what happens for?
Oh, so it has
Of the.
We have 3 leaves, so it's fine.
But then it's much larger. Oh, yeah.
Okay. Some of you are overcomplicating this. So what do? We don't do anything. We just flip the colors of the red. Okay? Yes? Right? So this is the correct, and I think you all have it, right? So this is what I was just talking about in terms of flipping these colors, because this is essentially what happens automatically when you go from your 2-3 tree to your LLRB. Okay, that's it. Those are the rules of getting to a BST. That's all you need to know. So what did we do? Let's think about the corrections we made. Okay? What were the 3 corrections we made? We'll go back. If we have so what's this one right here? Is this a problem?
Yeah.
So what's the problem? It's right leaning. All right, so we're gonna have rule 1. If we've got right leaning, what do we do?
Rotate top to left.
So we're gonna rotate, okay? Rotate left.
Rotate left. Oh, don't we have to specify?
Well,
We can't really.
we can't really specify. I can't say E as a generic rule, right? Okay, so we're gonna rotate left. Okay, what do we do when we have this structure? So there we're gonna color flip. And what do we want to call this thing? We'll just put color flip. Wow, it's fancy. Okay, and how about when we have this? What do we do here? So we rotate right. What do we want to call that? I gotta see I can't remember what he calls it. Rotate right.
Double insertion on the metal.
Yeah, so two, do they have to be left?
Or 2 to the right, I guess.
Thanks. Well, could we rotate right if there were 2 to the right?
Then you rotate back.
And can there be any red to the right?
No.
No. So we can only have 2 to the left, red, right? So we got 2 left links, 2 red links to the left. What are we going to do? We're going to rotate right. Okay. Okay. So right leaning 3 node. He calls it a left leaning violation. We're going to rotate left. That's rule 1. 2 consecutive left links. That's our bottom one. Incorrect 4 node violation. We're going to rotate right. And if there are any nodes with 2 red children, we have a temporary 4 node, we color flip. That's it. That's all we have to do to get an LLRB to be structured properly and correspond to a 2-3 tree. Sound good? Awesome. It's too late. Okay, so we're going to go through one of these and then I'll make you do some yourself. We're going to insert Z into this thing. Where does it go? Well, it comes over here and we color flip. Yeah? Cool. And we can see our corresponding, are we comfortable with our corresponding 2-3 trees? Okay. So if we insert Z, color flip Y, right leaning 3 nodes. So now when we did that, what's our problem with the top thing over there? What's our problem over here? Say again, Mary? It's a right red link. What do we need to do? Okay, so what are we going to rotate left? B, what happens then? I can't have a red right link, right? So we rotate, our rule says we rotate left. We're going to rotate left, the thing that's at the top of the red link, I guess we could say that. So B is going to come down to the left, S comes up. Does that correspond to this structure?
Yes.
Yeah, right. So I come down over here, I've got this thing, I rotate left B, and I get this. Is that the appropriate structure? Don't say sure. Is it yes or no? It's a yes or no, not a sure.
Yeah.
But why is, wait, which one? Why is,
Is that the thing on the right? Is that the correct corresponding structure to our 2-3 tree down here? Okay, someone who's saying yes, convince the people that are saying no.
Yeah.
Oh, wait, yeah, still the same.
Never mind.
There's
Wait,
still
can you
one
go back to
flat link away from the root.
Say again, Daniel, that's one rule is
There's still one flat link.
they're all still one block link away from the root. That's correct. Is my red link to the left? Do I have more than one?
So,
Yeah.
Does that look appropriate? Yeah, if I were to take this thing and draw it out, what would you do? Drop B down to the left and put a red link in, and it would take A and E with it. Okay. Try inserting those things into an initial empty LLRB. Okay, have at it.
then we do it in order of like what it is. Like 7.
Yep, 7, 6, 5, 4, 3, 2, 1 into an initially empty LLRB. See if you actually understand it. You guys can erase everything else that you got going on. Yeah, take turns drawing.
just draw it like this first and then see how it.
7, and then we can take 6. I think it goes on.
Here, I'll give you the,
7, 6,
And then by inserting red.
And then add 5. Doubling 5 and then.
Oh, we can. And I would have to, no, I know.
there's your rules.
What was the order again?
7, 6, 5, 4, 3, 2, 1. I think it's just straight through.
And then this is right. That's okay, right. So we have 2. Rotate right. We rotate 7 down to right.
But you gotta do it with the rows.
5, 6, 7. So erase this. So you're in no term.
Nice. The 2 join the 4. I mean, it's like this.
Yeah, and then
You have to put
7, 6, 5, 4. So red link 4.
Oh, right, you do
Right,
have,
then
no, so.
red link.
I mean, it's still the same
Oh,
thing,
yeah.
right? It's still
And then 5, 7. Rotate down.
No, but you have to say like rotate.
Five.
You have to say rotate.
So 4,
Right.
3,
That's whatever it is.
5. So.
Oh, you look at the rules of rotate.
Yeah, and then
Yeah, we're done.
Rotate, right?
Yeah.
Yeah. No, yeah.
And then
Oh.
2 and 1.
No, you're right. Why did you erase it?
We need to draw the backgrounds.
That's great, rotate, right? You have to show your rotate.
Then 3 goes, yeah.
Rotate, right, so.
1.
That's 3 and then now we have way more.
And this is 5.
Those two you have your rotate 5.
So 4 moves up,
4, 5.
6 goes down.
And
And
the 5 gets connected.
Rotate 5, right? And then.
Put in your steps. So as opposed to just drawing it out, like put in the steps that happen as you like these steps that you have to take. Obviously, you don't have to put the add steps in, but what do you do to get to your structure?
we make the drawing is.
So we had.
Or you can just put in the steps, whichever way you want to go. But that's the key part of this thing, is like, what are your steps to get there? Guess I'm not gonna worry about markers today.
Oh,
Rotate, right, and then come back. And then on this step,
On 5, so
this step,
rotate.
it was rotate.
But don't wait, like,
Yeah, rotate. Yeah, the-
No.
rotate.
Rotate.
Right. Next one. Good.
Then it would be rotate.
Two. That becomes 6. Oh, wait, not 5, that's 7.
Yeah.
oh, yeah.
Is that a color flip though? Because all we did was rotate.
Well, we changed the red links to black mid.
Oh, yeah.
Technically, you can see that was connecting to like the 6 on top, there's like visible on that. But there's like black thing, you're never just throwing.
Yeah, oh, so like,
Red color.
you see,
I don't think it's the right one.
The 3.
yeah, I'm pretty sure it was.
Oh, wait, let's draw the
So
red.
now
one.
rotate
Draw the red one.
4.
Oh, wait,
Next
can
color.
we let's check out the right line. That's the thing.
Also-
Yeah, that's good.
So someone write down my steps, you get from one piece to the next, so like the rotate, whatever you're doing.
The. Rotated 5 to the right.
Oh, rotate 6.
Yeah.
Oh.
Yeah,
Oh, it was 6, 5, 4, 3, so 5.
Yeah, I guess.
And then you add 2 to one.
If you write the rotate. Right,
So.
no, because we didn't draw the red line, so.
Oh.
For example.
You
on 6. Like 6,
So 2, this is 3.
7. We add 4 and 3. Yeah, and
Yeah.
then like 3 goes there, so actually 4 comes on.
No.
6 and like 4, 5, 4.
Oh, we forgot, it's still 2, 3. So we have to keep it.
Oh, rotate.
Up.
6 goes down to the right. 5.
Yeah.
Oh, rotate 5.
I think-
One goes up.
Yeah, okay, yeah.
Like 7 hours.
But I think you're supposed to keep.
Yeah.
Then wait.
Wait, Mr. Nkondo, it's supposed to be, like, when you finish it, it's supposed to be completely down.
Yeah. It should look like the corresponding.
So 2, 3, circle the push.
Like circle that, so that's.
Yeah, so, okay, so I'm pretty sure.
Oh, 5.
Pretty sure that you do.
Yeah.
5,
And then we
yeah.
have steps. Right? It was 7.
No, okay, it's definitely not that. Because.
2 and 1.
Yeah.
I would go down.
4, because 5,
So
no,
2 actually goes here. 3 goes here, 1 goes here.
So
Rotate right.
this is great, but the problem is we need to have the final end result be like this, because it's push out. So we have to have, it has to look like this.
Think about your numbers, stop, think about your numbers. Think about your numbers. That's your right and left, what that defines a binary search tree.
Here.
Oh, well.
Oh, wait.
Yeah, 6%.
Are we sort of repeating the same,
Oh, we had it right, look, we had it right.
are we repeating the same process several times?
Yeah.
Did we use recursion to do this?
Oh my.
And so we're just doing it.
Rotate right.
Wait, so we had it.
So we're sitting right one time, so we just, we're sitting right, like how would we do that?
Oh, yeah, so the step, the thing about you're not doing it again to an entire chart.
Yeah.
You're just doing it, so you just have some rules in your, where are we gonna have those rules? In add. As you're adding things,
Yeah.
right? Contains is gonna be the same as your binary search tree, everything else is gonna be the same. Right, it's just our add method does these rotations as we go through.
Would we have like a?
Because you're never gonna have like a random binary search tree and then say, hey, make this into an LLRB, it's just not gonna get in stone.
So we put like an add while this, okay.
Well, not even a while, right? Because
Because every time we.
you're just adding something, you're just gonna have a couple steps. Okay, so we get 7. What do we add? We had 6. Where does it go? It goes down and to the right, where it's left with a red link. We had 5. Where does it go? So what do I end up with? 2 left red links. So if I look over at my 2 left red links, what do I have to do? Rotate right. So what's going to happen? 6, right? 6 rotates up. Whoops. I don't get rid of this because then I can never find it again. I know that's stupid, but okay. So I get this, which is theoretically this thing, right? But I need to get to there. So I end up with 2 red links. What do? Color flip. What happens to the color? It's above, it goes away, right? Because I color flip and it goes away. Okay. I add 4, 4 goes down here. Are we good? Yep, that's fine. I add 3. I have the same issue, right? So now I have to, what theoretically happens in my 2-3 tree with this? Well, 4 goes up, so I have this, but I want to, yep, I've got 2 left red links. I rotate left 5, 4 comes up. So I get that. What do I do? Color flip, right? So the link becomes that. I add 2. I get this. Is this the correct tree from here?
Yeah.
It's fine, right? Because if I think about it, how far away is each leaf node? Each is 1, okay? And does 2 drop down? 4 drops down? Yep. 2 drops down? Yep, all good. Okay. And then I have to rotate right 3, same idea, right? And then what? Color flip, I get that. I add what?
Wait, for that, we just have to rotate right.
I don't get how you're flipping downward.
What do you mean?
How are you coloring flipping?
Because I've got 2 red nodes down here.
Yeah. And you want the red nodes.
So I color flip, so the color flip goes up here,
So you
just
color
like I did
flip-
with 6.
So you're calling color flip too?
Well, you're calling color flip on whatever has 2 red links going to it. So if I go backwards here, right, and I had 6, I have this one. When I rotated right 5, this comes down, but I've got 2 red links from 4 down to 3 and 4. And I have to color flip, so the red goes from here to here.
The one that has the 2 red ones.
Yeah, and again, what's the way to think of this? What's the way to think of this to make sure I've got it correct? This. I just think of the corresponding 2-3 tree. Is this what I want from this? Yeah, I just drop down 4 and make it a red link. So that's why I have to get the color flip.
Could we just like create your 2-3 tree first and then like just create the links for there and be faster?
Why can't I do that? One more time. Why can't I just create the 2-3 tree? You can't implement the 2-3 tree. That's the whole point of this process, right? 2-3 tree is just too hard to implement. So, Logan, stop writing. Okay, so we're back here. We rotate right 3. We got this. We color flip. We get this. Now what do we have? We have 2 red left links. After I do this color flip, I've got these 2 red links. I can't have 2 left green links. What do I do?
Rotate right 6.
Rotate right 6
Or
4
No, 6.
or 6? Which one?
6.
6. Right? Because what do I want to have happen? 6 to come down and to the right. 4 goes up. But what happens when that happens? What just happened to 4? This is a little tricky.
4 joins with 6.
4 joins with 6. Okay, but now what is, when I drop 6 down, what happens to 4 now? But how many children does 4 have? Think about it.
It's pretty.
It's got 3 children. Can I have 3 children?
Oh.
So what has to happen?
I guess 6.
The 5 has to transfer over, right? So I come up, if I redraw this thing, 4 comes up with 6, right? 6 comes down over here, but 4 still has 2 and 5. And 6 has 7. So what has to happen?
5 joins 6.
Yeah, 5 has to come over to this side. To keep the binary search tree properties, right? Because 5 can't be on the left of, or they can't be down here with 6 over there. Yes or no? Okay, so we get this. Wait, what?
Yeah, they rotated right 6.
But why did this go happen?
That was the original one. And then you added 1. And then that's before we added 1.
Oh, okay. Okay, rotate right 6, thank you. I'm like, wait a minute, why do I have a red link down? It moved down. Okay, so we do that, we get this, and what do? We color flip. Right, we're sort of glossing over the fact that the 5 skips over to the 6 here, but whatever. And we color flip floor, and we get that. So what do we end up with? Perfectly bushy BST. Cool. That's it. That's all she wrote. Yep.
Color flip like the red links from 2 to 4 and 6 to 4. Since there's nothing above 4, do they just go away?
Yep. They do. It depends on how you've structured it, right? Do we think we're going to have a link to our root node? Maybe. In which case, would you just make the link to the red node red, or link to the root node red? Too many R's. Yeah, you would just flip it and put it up there. Okay. Otherwise, regardless, it's sort of, we just don't visualize a link to the root node, even if we happen to have one. Yeah.
I'm confused just on the last steps too, because isn't it the rule like no red links better to the right?
Which step are we talking about?
Six, like, 6. The 2 and then like 4.
This?
Yeah, but then that's still there's like the red link in 26.
Yep. Which is what we had every time we did the rotate right. Right. So if I come back up to this, right? What did I do when I rotate right? 5 drops down, 4 comes up, and I end up with 2 red links. I temporarily end up with this. So what do I have to do? Color flip.
So we did.
So I'm just doing the exact same thing. Anytime you do this, right, you're temporarily creating this thing that doesn't work. That's why we have to color flip.
So we can like momentarily break the rules to fix it.
Basically, but we got to remember, are the red links actually there? Not really. They're just there to help us think about what the structure should look like, right? That's all it is. It's a conceptual tool to use to figure out how to get from here to here. Okay, so yeah, we temporarily break the rule, and when we do that, we know we have to color flip.
What about like in the end, like when you rotate 6 to the right, like you can't color flip and you end up with like 2.
Well, we can color flip.
Okay.
That's what we were just talking about a minute ago.
Oh.
Yep.
Nothing above it.
There's nothing there,
Oh.
right? Depends on your implementation of how you structured it. Again, could we have a theoretical red link to our root node? Yes. Okay.
So why don't we just, I know you said we just theoretically combine 5, like connect 5 and 6, but like why?
I'm sorry, one more time?
So we can just connect, because you said we can just say that we're connecting 5 and 6. And that.
You can just say you're connecting 5 to 6? No,
But like, I don't know how.
I'm not, your question, I'm not understanding your question.
So when you rotate right, the 5 automatically connects to 6 because it's like, if there's a right child that's connecting to the new to the new root, then its right child becomes connected to the 6 that rotated right.
Oh.
Okay, so when I do this step, this is the step we're talking about, right? So I rotate right 6. What happens to 6, Alex?
It goes down
It goes down into
the right.
the right. Okay, so what happens to 4?
Goes up.
4 goes up. Well, if I have 4 going up, how many children does 4 have?
2.
2. And when I send 6 down, what does 6 become?
A shot.
A child of
4.
4. Can I have 3 children? No. But I know for a fact that 6 has carried with it how many children? 1. So I know that 6 is going to take 7 with it. So I know 5 theoretically should be there. It's just in your implementation, you actually have to make that step.
Oh, you have to like say.
You have to physically, do I have to physically reconnect that? Yes. It's just one extra step in that particular process. If the thing, so if 4 didn't have, if it was like this, we wouldn't have any issues. But if 4 has 2 children, I have to take that extra step and move its right child to be the left child of the thing moving down. It's just part of the implementation.
So they're just redefined.
So like, we're adding, this time we're adding 7, 6, 5, 4, 3, 2, 1, we're doing, is there other implement, or other like sequences that we would add that would cause us to do something?
So do something like what?
Move, attach 5 to 6. Like any other sequences.
We could probably come up with, sure.
Oh, okay.
I can't visualize them in my head, like, I'm not on a Tuesday morning at least. But yeah, so right, so just, the point is that could I add these in any order? And what 3 rules do I need? Those. These 3 rules take care of all of our adds to an LLRB. To give us a bushy binary search tree. That makes sense? Because again, where do am I gonna give you a random, is anyone gonna give you a random tree and say, hey, make this an LLRB? No, we're gonna construct this thing, right? And where do these rules take place? In your, just in add. Do I need to worry about them anywhere else? Theoretically, where do I sort of need to worry about? Delete.
Oh.
We're not gonna deal with delete because delete is a nightmare, to be honest. Like it's not a nightmare, it's much more complicated, right? But with these 3 rules, we can create an add method. I just need to keep in mind when I do this one move, when I rotate right, and I've got an extra child, I just need to account for that. Yeah, Dave.
So these red black trees are the things Java uses.
This is the Java implementation, so we can actually look at it. People can sit down for the last couple of minutes here. Since I've had you standing the whole time, I will show you the Java implementation because it's kind of cool. Here we go. This is the actual Java class for tree map. And what do you notice about Java's implementations of these things? This is the actual JDK. This is the class. What do you notice? There's a lot of like it's mostly comments. Okay, we're going to see lots and lots of code, and it's mostly comments. Okay, so we got a map in here. We've got a comparator. We've got our K's and V's. We've got some sort of a transient int mod count. Okay, and where do we get to the important parts here? It's a tree maps. Sort, build, sorted frame. Yeah, that's not very useful. Contains, get, we want to put, right? Because get and put should be pretty easy. Last key, first key, put. That's put all. We don't want put all. We want get entry. Entry. Okay. Yeah. There's a lot of things in here. Thankfully, we don't have to implement when we build things. Get floor entry. Don't have to do that. Get higher entry. It sounds like, you know, I don't know what it sounds like, but okay. Get higher entry. That's what we want. Put. Okay. If t equals null, we compare our keys. We're going to go through and we're going to essentially, let's see if we can figure out what we got going on here, right? If our comparator is not null, we're going to put our child to the right or the left. Same. Fix after insertion. Okay, so clearly where are we going to find our 3 rules? Fixed after insertion, right? So we've just stuck it where it's supposed to go, and then we got to go find the fix after insertion. And then again, we're not going to deal with that. We're going to go find fix after insertion, first entry, last. Weeks. Okay, thankfully. Maybe we'll find fix after insertion. That would be easier, wouldn't it? But I'm so curious to see all the things that are in here. Descending map, submap, head map, tail map. There we go. More submaps.
How long is this?
It's a good question. How far? We're about halfway through it. Like we're about a third of the way through the
Like 3,000.
probably 3,000 lines. Yeah, contains. I got lost as to where we were. Splitterator. We got a splitterator. Contains, remove. Okay.
Fix after insertion.
Yeah. Oh, but it's not, it's
You
just,
can, press enter.
oh, there we go. Okay. While this is not null and it's not the root and it's parent color equals red. So there we go. They actually are giving us, they're using colors, okay? So parent color equals red, if parent of equals left parent of. Then if the color equals red, we're gonna set the color black. Parent of is red. So what did we just do there? Looks like a color flip to me if I not, that looks like the color flip there. Otherwise, oh, there we go. Right of parent of X. We're going to rotate left. We're setting the color black. There's our rotate left. Okay. Okay, rotate right is here. Right, so if we have, it looks like if we have left of parent of X, color's red, then we're going to, this is where, I guess, I think it looks like they're maybe doing color flip and this is the two lefts, right? So if we've got two lefts, we're rotating right. And what do we have to do when we do that? Color flip. So it looks like they're wrapping it into one. Okay. Cool. It's kind of fun to see it in action. And let's just, I'm curious, let's see. It's just around 3,000 lines of code. No, I mean, most of it's code down here, right?
Beginning.
It's just in the beginning, there's probably several hundred lines of code of comments.
Those just explain them.
Yeah, and you'll see, I mean, even in the middle here, right? The best base class for splitterators, right? So again, there's a lot of commenting of code with your splitterators. Who knew? Okay, have an awesome rest of your day. I am going to throw some homework in there, and I don't get to see you. Oh no, I see you on Friday.
Oh, yeah.
We have Thursday symposium, so no Thursday class. I'm going to see if I can find a leak code for LLRBs, because I think that would be fun. I tried to find one for red black trees. I tried to find one for 2-3 trees, but there weren't any in there. Yep. Red leaning. I mean, theoretically, you could structure the whole thing right leaning. Yeah, you just have to change it all. So I think just the computer science world has decided that it's left leaning and that makes life easier.
And it's easier to say LLRB
Then
than RL.
Exactly. Have a good day.
RLRBBS.
Yeah. That's what you're gonna have for lunch.
Thank you, Mr. Mel.
All right. Have a great day, everybody. I'll see you later.